Something strange is happening in the depths of space, something that defies everything we think we know about the universe. Galaxies millions of light years apart are moving in ways they shouldn't, pulled by invisible forces that leave even the brightest minds in astrophysics utterly baffled. This isn't just a cosmic coincidence. It's evidence of something far more mysterious lurking in the shadows of the cosmos: dark matter, an enigmatic substance that makes up nearly 85% of the universe's mass, yet remains completely invisible to our telescopes. It doesn't emit light, reflect it, or interact with ordinary matter in any way we can directly observe, and yet its gravitational pull is so powerful it bends the very fabric of space itself, orchestrating the movement of galaxies like a hidden conductor guiding an unseen symphony. Imagine standing on a shore, watching the tide roll in, except there's no moon in the sky to explain the waves. That's the unsettling reality scientists face when they study dark matter flows. These vast rivers of invisible matter stretch across the cosmos, weaving through galaxies and galaxy clusters with a force that shouldn't exist. Some of these flows span hundreds of millions of light years, carrying entire clusters of galaxies along like leaves caught in a cosmic current. What's creating these currents? Why do they move the way they do? And what does it mean for the fate of our universe? These aren't just questions for astronomers. They're puzzles that could rewrite the laws of physics as we know them. Today, we're diving headfirst into 25 of the most mind-bending mysteries surrounding these dark matter flows. From the Great Attractor, a mysterious gravitational anomaly pulling thousands of galaxies toward it, to the eerie voids where dark matter seems to vanish entirely, we'll unravel the secrets of this invisible force shaping our universe. You'll discover how scientists hunt for something they can't see, why dark matter might be stranger than we ever imagined, and what these hidden currents reveal about the origins and ultimate destiny of everything around us. This isn't just a tour of cosmic oddities. It's a journey to the edge of human understanding, where the answers we find might be more shocking than the questions we started with. So buckle up, the universe is about to get a whole lot weirder. One of the most startling proofs of dark matter's existence came from a cosmic accident, a violent collision between two massive galaxy clusters known as the Bullet Cluster. When astronomers first observed this spectacle, they expected the visible matter, the glowing clouds of hot gas, to align with the gravitational pull distorting the region. But something unexpected happened. The gas, slowed by friction, lagged behind, while the bulk of the mass, revealed by gravitational lensing, surged ahead as if something invisible were carrying it. That something was dark matter, a substance that doesn't just refuse to interact with light, it barely interacts with itself. This discovery turned astrophysics on its head. Normally, when galaxies collide, everything stars, gas, dust gets tangled together. But here, the dark matter sailed straight through the chaos, leaving the ordinary matter behind. It was like watching two crowds of people crash into each other, only to see their shadows keep walking unfazed. This bizarre separation gave scientists their first direct evidence that dark matter wasn't just a mathematical fix for missing mass. It was real, it was massive, and it played by its own rules. Yet for all it revealed, the Bullet Cluster deepened the mystery. If dark matter barely interacts with anything, how does it shape the universe so precisely? Why does it cluster around galaxies like an invisible skeleton, holding them together? And most puzzling of all, what is it? Decades later, we still don't have answers, only more questions. Some theories suggest undiscovered particles, while others propose modifications to gravity itself. But one thing's certain, this cosmic traffic accident didn't just prove dark matter exists, it showed us how little we truly understand. If our current understanding of dark matter is correct, the Milky Way should be surrounded by a swarm of thousands of tiny dwarf galaxies, cosmic crumbs left over from the formation of our galactic neighborhood. Supercomputer simulations paint this exact picture, showing vast halos of dark matter clumping together and pulling visible matter into orbit. But when astronomers peer into the night sky, they find only a few dozen of these satellites. This glaring mismatch between prediction and reality is called the missing satellite problem, and it's one of the most persistent headaches in modern astrophysics. One leading theory suggests the answer lies in the very nature of dark matter itself. Most models assume dark matter is cold, meaning its particles move sluggishly, allowing them to clump easily into small, dense structures like dwarf galaxies. But if dark matter were slightly warmer with particles zipping around faster, these smaller clumps might never form. It's like comparing sand to flour. One piles neatly into tiny mounds while the other stays loose and diffuse. Some researchers argue this warm dark matter could explain why we're missing so many satellites, as the faster-moving particles would smooth out the smaller density variations needed to birth dwarf galaxies. Another possibility is even more radical. What if our theories about gravity itself are incomplete? Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently on cosmic scales than our equations predict. In this scenario, dark matter might not exist at all, and the missing satellites could be a sign that gravity's rules need rewriting. But MUND has its own challenges, like explaining phenomena such as the bullet cluster where dark matter's influence seems undeniable. The plot thickens when we consider that many of the dwarf galaxies we do observe seem suspiciously dark matter-rich, as if they're the rare survivors of some cosmic filtering process. Could tidal forces from the Milky Way have torn apart the rest, or are we simply not seeing them because they're too faint? New telescopes like the Vera Rubin Observatory may soon spot these ghostly remnants hidden in plain sight. Until then, the missing satellite problem remains a glaring hole in our cosmic map, a reminder that even our best models might be missing something fundamental about the universe's hidden architecture. Picture the universe not as a random scattering of galaxies, but as an impossibly vast spiderweb, threads of invisible dark matter stretching billions of light years across the cosmos, connecting everything like celestial scaffolding. This is the cosmic web, the hidden architecture of existence itself. While we see galaxies glittering like dewdrops on this web, the silk itself remains utterly invisible. Yet without it, the universe as we know it would collapse into chaos. These filaments of dark matter aren't just passive threads, they're dynamic highways shaping the destiny of galaxies. Computer simulations reveal how gravity causes ordinary matter to flow along these invisible tendrils, pooling at the intersections where galaxy clusters form like beads on a string. It's as if the universe is following a blueprint we can't see, with dark matter acting as both architect and construction crew. The result: a stunningly organized large-scale structure where galaxies align along these cosmic threads in a pattern so precise it defies coincidence. But here's where things get eerie. While we can map the web's outline by studying galaxy distributions, the filaments themselves leave no trace. They don't absorb or emit light, and efforts to detect their faint gravitational lensing effects push telescopes to their limits. It's like trying to study a sculpture by only observing the dust settling on its surface. Some researchers have attempted to illuminate these shadows by tracking ultra-fast particles called cosmic rays, which may travel along dark matter highways like messengers revealing an unseen path. Others look for subtle temperature variations in the cosmic microwave background, the afterglow of the Big Bang, which might bear the fingerprints of dark matter's gravitational tug. The most puzzling aspect: this web shouldn't be so uniform. According to conventional physics, dark matter's lack of interaction should make it clump randomly. Yet the cosmic web displays startling symmetry, with filaments spaced at remarkably regular intervals, like some fundamental law we haven't discovered yet is weaving order into the darkness. Could there be an unknown force guiding this structure, or does dark matter interact in ways we've yet to imagine? every new cosmic map deepens the wonder, showing us a universe far more intricate and far stranger than we ever dreamed. Astronomers recently uncovered something that shouldn't be there: monstrous galaxies from the universe's infancy, so massive and fully formed they defy every prediction about how cosmic structures grow. These celestial behemoths, spotted when the universe was less than 10% of its current age, contain hundreds of billions of stars packed into sprawling disks that, according to our best models, simply wouldn't have had enough time to assemble. It's like finding a skyscraper in the middle of the Stone Age, an architectural marvel appearing far too early in history to make any sense. At the heart of this puzzle lies dark matter. Current theories suggest these invisible halos should have acted like cosmic glue, slowly pulling gas clouds together over billions of years to form galaxies. But these ancient titans appear to have sprung up almost overnight, their stars crystallizing at speeds that leave physicists scratching their heads. One leading explanation proposes that patches of the early universe might have contained freakishly dense concentrations of dark matter cosmic seeds, so massive they turbocharged star formation. Imagine trying to grow a redwood forest. Normally, you'd expect decades of slow growth. But if someone had secretly buried super fertilizer beneath the soil, those trees might shoot up in months. That's the kind of anomaly we're dealing with in space. The trouble is, even this explanation creates new mysteries. Dark matter isn't supposed to clump that efficiently in the early universe. According to supercomputer simulations based on the Standard Model, matter distribution after the Big Bang should have been relatively smooth, like a freshly poured pancake batter, with only subtle ripples that gradually amplified over time. Yet these ultra-dense pockets imply an unevenness in the primordial universe that our models don't account for. Some scientists speculate that dark matter might have unexpected properties. Perhaps certain regions had exotic particles that interacted more strongly, creating gravitational hotspots where galaxies could blossom unnaturally fast. Even more perplexing, many of these too-big-to-exist galaxies show signs of having already burned through their star-forming fuel by the time we observe them, meaning their frenzied construction phase happened even earlier than we can currently see. It's as if we're catching the final act of a play that started before the theater doors even opened. Upcoming telescopes like the James Webb Space Telescope are peering deeper into this cosmic dawn, hunting for even earlier examples that could force us to rewrite the timeline of galaxy formation entirely. What makes these ancient giants so crucial isn't just their shocking size. It's what they reveal about dark matter's hidden behavior. If our current models can't explain their existence, we might be missing a fundamental piece of the puzzle. Perhaps dark matter isn't as passive as we assumed, or maybe gravity worked differently in the universe's infancy. Either way, these galactic titans stand as cosmic roadblocks, forcing us to question whether the invisible scaffolding of the universe is far stranger than we ever imagined. Deep in the cosmos, something is pulling, not just one galaxy or cluster, but hundreds, all streaming in the same direction at breakneck speeds, as if caught in some universal undertow. Astronomers call this phenomenon the dark flow, and it's one of the most unsettling puzzles in modern cosmology. These galaxy clusters aren't just drifting apart with the universe's expansion. They're racing together toward a point beyond the edge of everything we can see, defying the rules of how matter should behave on such colossal scales. The first hints emerged when scientists studied the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature variations in this ancient light revealed something bizarre. Galaxy clusters weren't just moving randomly, they shared a common velocity, all hurtling toward a mysterious region of space roughly 3 billion light-years away. That's like every leaf in a forest suddenly blowing in the same direction, even though no wind is detectable. The scale of this motion is staggering. Some clusters are barreling forward at nearly 2 million miles per hour, their paths aligned with an eerie precision that shouldn't be possible. Now here's where things get really strange. According to our standard model, the universe's expansion should be the dominant force on these scales, with galaxies drifting apart like raisins in rising dough. Gravity from visible structures, things like superclusters or great walls of galaxies, can't explain this coordinated movement. The dark flow suggests something else is out there, something so massive and distant that its gravitational reach extends beyond our observable horizon. Some theorists propose it could be a superstructure from another universe, a cosmic neighbor in the multiverse tugging at ours like a magnet hidden behind a curtain. But not everyone's convinced. Skeptics argue the dark flow might be an illusion, a statistical fluke or a measurement error amplified by the challenges of tracking motion across such vast distances. Others suggest it could point to gaps in our understanding of gravity, hinting that Einstein's equations break down on scales larger than we've tested. After all, we've never directly observed gravity's behavior across billions of light years. Could there be hidden terms in the equations, some cosmic correction we've missed? The most tantalizing possibility, that the dark flow is evidence of a pre-Big Bang structure, a relic from whatever existed before our universe began. If true, it would mean our cosmic horizon isn't just a limit of observation, but a literal boundary between our universe and something older, vaster, and utterly alien. Future missions like the European Space Agency's Euclid telescope aim to map this motion with unprecedented precision, potentially settling the debate once and for all. Until then, the dark flow remains a ghostly signal from the unknown, a current in the cosmic ocean, pulling us toward answers we aren't yet equipped to understand. Our galaxy, the Milky Way, should be perfectly balanced, a cosmic spinning top wrapped in a spherical halo of dark matter. But something's off. Recent observations reveal our dark matter halo isn't the symmetric shell we expected. It's warped, lopsided, almost as if some colossal force yanked it sideways. This isn't just a minor irregularity, it's a full-blown contradiction of one of astrophysics' core assumptions. If dark matter behaves as we think it should, gravity would have sculpted it into a smooth, even cocoon around our galaxy. Yet the Milky Way's halo looks more like a deflated football, bulging mysteriously on one side. The leading suspect, a past collision, one violent enough to leave a gravitational bruise on our galaxy's invisible framework. Scientists have traced the orbits of nearby dwarf galaxies, like the Large and Small Magellanic Clouds, and found their paths suspiciously aligned with the halo's distortion. These satellite galaxies might be more than just cosmic hitchhikers. They could be the wrecking balls that knocked our halo out of shape. Picture swinging a heavy purse in circles around your body. Even though the purse is small, its momentum would tug your posture off balance. Now imagine that purse is a dwarf galaxy, and your body is the Milky Way's trillion-ton dark matter halo. The math suggests these galactic companions, with their combined pull, could have warped the halo's structure over billions of years. But there's a twist. Some simulations show the Magellanic Clouds might not be massive enough to cause this distortion alone, unless dark matter interacts with itself in ways we haven't accounted for. Normally, dark matter particles are thought to pass right through each other like ghosts. But if they occasionally scatter or collide, even weakly, that extra friction could amplify the dwarf's gravitational influence, leaving a more pronounced warp in their wake. It's like realizing the invisible ink you've been studying isn't just transparent. It's slightly sticky, retaining impressions from touches you never noticed before. Another possibility is even more dramatic. The Milky Way's halo might bear scars from an ancient, head-on collision with another galaxy. Imagine throwing a pebble into a pond. The ripples spread outward in rings, but they also rebound inward, creating complex interference patterns. A major galactic merger, like the one that likely formed our galaxy's thick disk around 10 billion years ago, could have sent similar shockwaves through the dark matter halo, leaving permanent wrinkles in its structure. The implications go far beyond our galactic backyard. If asymmetrical halos are common, it could mean our entire understanding of dark matter's behavior is incomplete. Maybe it's not as passive as we thought, or perhaps galaxies grow through more chaotic mergers than simulations predict. Upcoming missions like the European Space Agency's Gaia spacecraft are mapping the motions of billions of stars with unprecedented precision, hunting for subtle gravitational clues that might reveal how this invisible scaffold got bent out of shape. The Milky Way's warped halo isn't just a curiosity, it's a cosmic crime scene, and the fingerprints left behind could rewrite the rules of the universe's hidden architecture. In the 1970s, astronomer Vera Rubin made a discovery that shattered our understanding of how galaxies move. By meticulously measuring the speeds of stars in Andromeda, she found something impossible: stars on the galaxy's outskirts were whipping around just as fast as those near the center. According to Newton's laws, these outer stars should have been slowing down, like planets in our solar system where Mercury orbits far quicker than Neptune. But Rubin's data showed no such drop-off. The only explanation: some invisible mass must be lurking in the galaxy's halo, providing extra gravitational glue to keep those stars speeding along. This was the first concrete evidence of dark matter's existence, a revelation that rewrote the textbooks overnight. Yet decades later, a stubborn mystery lingers. While dark matter models successfully explain Rubin's original observations for most large spiral galaxies, some modern studies reveal systems where the theory still falls short. Take ultra-diffuse galaxies, ghostly, faint systems with stars spread so thin you could look right through them. These cosmic wisps rotate far slower than predicted, as if they're missing huge chunks of their dark matter halos. It's the opposite problem Rubin identified, like finding a car with its gas pedal floored but barely moving. Even stranger are certain compact galaxies where stars spin so fast they should fly apart, yet somehow hold together with seemingly no dark matter at all. Theories abound to explain these mismatches. One fascinating idea suggests dark matter might be sticky, not just invisible, but capable of interacting with itself through unknown forces. In this scenario, collisions between dark matter particles could have ejected them from smaller galaxies over billions of years, like a cosmic game of pinball where the balls gradually vanish from the machine. Alternatively, tidal forces from passing galaxies might have stolen their dark matter, leaving behind visible stars like a fruit stripped of its peel. But the plot thickens when we consider that some of these anomalies appear linked to a galaxy's environment. Dense galaxy clusters show more mismatches than isolated systems, hinting that dark matter's behavior might change depending on its cosmic neighborhood. Could there be different flavors of dark matter, some more prone to clumping or dispersing than others? Or is our understanding of gravity itself incomplete at certain scales? Modified gravity theories propose tweaking Newton's equations to eliminate dark matter entirely, but they struggle to explain phenomena like the bullet cluster where dark matter's fingerprint is undeniable. Rubin's rotation curves opened a door to the invisible universe, but behind it, we're finding not just answers but deeper layers of questions. Every galaxy that defies expectations is like a discordant note in a symphony, hinting that the composition of the cosmos might be more complex than we imagined. Upcoming telescopes designed to map dark matter in unprecedented detail may finally resolve whether these mismatches stem from flaws in our models or from something far more extraordinary hidden in the shadows. For decades, scientists assumed dark matter must be cold, composed of slow-moving, heavy particles that clump together easily to form galaxies. This cold dark matter model works beautifully on cosmic scales, predicting the large-scale structure of the universe with uncanny accuracy. But zoom in closer and problems emerge. Galaxies appear less clumpy than they should be, with fewer satellite companions than simulations predict. It's like expecting a rugged mountain range but finding gently rolling hills instead. Enter an intriguing alternative: warm dark matter particles just a fraction lighter than their cold counterparts, giving them enough speed to smooth out those problematic small-scale wrinkles in the cosmic tapestry. The difference boils down to motion. Imagine two types of paint spilled on a canvas. Cold dark matter behaves like thick oil paint, piling into distinct globs that hold their shape. Warm dark matter acts more like watercolor, still forming patterns, but with softer edges as the faster-moving particles resist clustering too tightly. These slight speed differences could explain why we don't see the dense swarm of tiny satellite galaxies our models expect around the Milky Way. Warm particles would have zipped straight through the early universe's denser regions, suppressing the birth of smaller structures while still allowing massive galaxies to form. Yet warm dark matter comes with its own paradoxes. While it fixes the missing satellites problem, it struggles to explain how the first galaxies formed so quickly after the Big Bang. Cold dark matter's sluggishness lets it collapse rapidly into dense halos where stars can ignite, but warmer particles would delay this process. It's like comparing two construction crews, one using pre-built modules that snap together overnight, another mixing concrete from scratch. The latter might build a sturdier foundation, but it takes longer to get started. Some researchers propose a compromise. Maybe dark matter isn't purely cold or warm, but a mix of both, a cosmic cocktail where different particle types dominate at different scales. The most promising warm dark matter candidate, sterile neutrinos, hypothetical cousins to the nearly massless neutrinos we've already detected. These particles would be thousands of times heavier than regular neutrinos, yet still light enough to move at a significant fraction of light speed in the early universe. Experiments like the upcoming Japanese comet project aim to detect signs of these elusive particles, which could decay into detectable X-ray photons. If found, they'd revolutionize our understanding of dark matter's nature, not as a single mysterious substance, but as a diverse family of particles with varied properties. What makes this debate so compelling is that both models, cold and warm, have moments where they shine and others where they falter. Cold dark matter predicts the cosmic web's grand architecture flawlessly but stumbles on galactic details. Warm dark matter cleans up small-scale inconsistencies yet can't easily explain the universe's fastest-forming giants. It's a reminder that dark matter might be more complex than we've assumed, behaving differently in various cosmic environments. Like two competing theories of light particle and wave, the truth could lie somewhere in between, waiting for a deeper theory to unite the pieces. Until then, the hunt for dark matter's true identity remains wide open, with warm particles offering a tantalizing path through the labyrinth of cosmic mysteries. In the frozen depths of space, astronomers have stumbled upon a cosmic anomaly so baffling it challenges our fundamental understanding of the universe's structure, the Eridanus Supervoid. This colossal region of space, spanning nearly 2 billion light-years, is so empty it defies logic. But what makes it truly eerie is its connection to the cosmic microwave background, the afterglow of the Big Bang, where it appears as a chilling, cold spot, a patch of sky inexplicably cooler than its surroundings. This isn't just a minor temperature fluctuation. It's a blistering red flag in our cosmic map, screaming that something, perhaps dark matter's hidden hand, is warping the fabric of reality itself. At first glance, the explanation seems straightforward. Supervoids, vast regions with fewer galaxies and less matter, should naturally cool light passing through them due to a phenomenon called the integrated Sachs-Wolf effect. As photons traverse these underdense regions, they lose energy climbing out of the void's weakened gravitational pull, creating a cold imprint in the cosmic microwave background. But the Eridanus Supervoid is different. Its cold spot is too cold, up to 70 microkelvin chillier than standard models predict. It's like walking into a forest and finding one tree radiating frost in the middle of summer. The numbers simply don't add up. Here's where dark matter enters the mystery. If this void isn't just empty space but a region where dark matter is also unusually sparse, its gravitational effects might amplify the cooling. Imagine dark matter as an invisible scaffold. Remove too many beams, and the structure warps unpredictably. Some simulations suggest such ultra-deep voids could exist if dark matter clumps in ways we haven't accounted for, leaving behind cosmic holes where both normal and dark matter are scarce. But even this theory struggles to explain the cold spot's extreme temperature dip. That leaves an even more radical possibility. The cold spot might not be a void at all, but evidence of a cosmic bruise, a collision with another universe in the multiverse. Certain bubble universe theories propose that our cosmos could have bumped into another during its inflationary phase, leaving behind a gravitational imprint that cooled the cosmic microwave background. It's a breathtaking idea, proof of a reality beyond our own etched into the sky. Yet skeptics argue the cold spot could just be a statistical fluke, a cosmic mirage caused by the sheer scale of our observations. The debate rages because the stakes couldn't be higher. If dark matter's distribution explains the anomaly, we're missing key details about how it sculpts the universe's largest structures. If it doesn't, we might need entirely new physics, or worse, admit we've been wrong about dark matter all along. Upcoming galaxy surveys like the Dark Energy Spectroscopic Instrument are mapping the void's true dimensions, hunting for hidden matter that could solve the puzzle. Until then, the Eridanus cold spot remains a cosmic Rorschach test, its meaning as elusive as the dark matter that may or may not lurk within it. Deep beneath mountains and abandoned mines, in laboratories shielded from cosmic rays, scientists have spent decades listening for whispers from the dark. Giant vats of liquid xenon, ultra-pure crystals, and tanks of frigid argon sit in silent vigil, waiting for the slightest tremor, a signal that a dark matter particle has finally brushed against ordinary atoms. Yet after 30 years of searching, the detectors remain stubbornly quiet. This is the unsettling paradox of dark matter. We see its gravitational fingerprints everywhere in the cosmos, but when we reach out to touch it directly, our hands close on empty air. The primary suspects in this cosmic detective story are WIMP weakly interacting massive particles. Theory suggests these hypothetical particles should weigh somewhere between 10 and 1,000 times more than a proton, barely interacting with normal matter except through gravity and perhaps the weak nuclear force. Their sheer abundance could explain dark matter's dominance in the universe, with trillions streaming through your body every second without a trace. The logic seemed flawless. If WIMP exist, sensitive enough detectors should occasionally catch one bumping into an atomic nucleus, like hearing a single pin drop in a silent auditorium. But despite ever more sensitive experiments, from Italy's Gran Sasso Lab to South Dakota's Sanford Underground Research Facility, not one unambiguous WIMP signal has emerged. So where does that leave us? One possibility is that WIMP are even more elusive than predicted, interacting so weakly that our current technology simply can't register their touch. It's like trying to catch smoke with a net woven too coarsely. The particles slip through unnoticed. Another, more unsettling idea is that WIMP don't exist at all, and we've been chasing a phantom. This has led researchers to explore alternative candidates, with one rising star being Action's ultralight particles, originally proposed to solve a puzzle in quantum physics. Unlike bulky WIMP, Actions would be billions of times lighter, behaving less like discrete particles and more like a pervasive cosmic wave. The Action hypothesis offers intriguing advantages. Their low mass means they'd naturally occur in vast numbers to account for dark matter's heft, like needing countless feathers instead of a few boulders to balance a scale. More crucially, Actions might interact with electromagnetic fields in ways WIMP don't, offering new detection strategies. Experiments like the Action Dark Matter experiment ADMX use powerful magnets to convert Actions into microwave photons, essentially turning the particles into faint radio signals we can tune into. Early results are promising, though still inconclusive. Yet even as the search branches out, the silence raises deeper questions. Could dark matter be something even stranger, particles that don't interact at all except through gravity, making them effectively invisible to any detector we can conceive? Or might the answer lie beyond particles entirely, in modifications to gravity or hidden dimensions? The longer the detectors stay quiet, the more we're forced to confront an uncomfortable truth. Dark matter may not just be hiding in the shadows of space, it might be hiding in the blind spots of our imagination. Every null result is a clue, not a failure, pushing us to think more creatively about the invisible architecture of the universe. What if dark matter isn't just a cosmic oddity, but the silent architect of life itself? The delicate balance of our universe hinges on forces we can barely detect, and dark matter's gravitational embrace might be the reason galaxies like the Milky Way exist in a state perfect for nurturing planets and life. Without it, stars would fly apart, spiral arms would unravel, and the stable orbits that allow planets to bask in their sun's warmth for billions of years would vanish like smoke in the wind. Consider Earth's position in the galactic suburbs, far enough from the chaotic core to avoid deadly radiation, yet close enough to benefit from a rich supply of heavy elements forged in ancient stars. This ideal location isn't accidental. Dark matter's invisible scaffold holds our galaxy together with such precision that even a slight shift in its distribution could send solar systems like ours spiraling into the void or crashing toward the crowded, violent center. It's as if the universe calibrated dark matter's presence like a thermostat, ensuring just enough gravitational glue to maintain order without smothering the delicate chemistry of life. But here's the spine-tingling implication. This just right arrangement echoes something called the anthropic principle, the idea that the universe's fundamental constants appear fine-tuned for life's existence. Dark matter's behavior is no exception. If its particles interacted even slightly more with ordinary matter, stars might never have formed. If its halos were less diffuse, galaxies could have clumped into dense knots where stellar collisions would sterilize entire regions. The fact that we find ourselves in a galaxy where dark matter's pull is neither too strong nor too weak feels less like coincidence and more like a prerequisite for our very existence. Some scientists take this further, suggesting dark matter might play an even more direct role in life's origins. Certain theories propose that dark matter particles drifting through Earth could subtly influence chemical reactions, perhaps even guiding the intricate molecular dances that led to the first self-replicating cells. Others speculate that dense dark matter filaments may have funneled comets and water-rich asteroids toward early Earth, delivering the building blocks of life. While these ideas remain speculative, they underscore a profound truth. The universe's greatest mysteries might be intertwined with our own existence in ways we're only beginning to grasp. Yet for all its apparent fine-tuning, dark matter's story isn't one of perfect harmony. Across the cosmos, galaxies exhibit startling variations in their dark matter content, from ghostly systems nearly devoid of it to others drowning in unseen mass. If dark matter were truly designed for life, why such inconsistency? This cosmic unevenness suggests another possibility. Perhaps we don't live in a universe fine-tuned for life, but in one of countless realities where dark matter's distribution happened by chance to permit our existence. The alternative, that dark matter's properties are somehow necessary, raises even deeper questions about whether life is a fluke or an inevitable outcome woven into the fabric of physical law. As telescopes map dark matter's hidden web with ever greater precision, each new discovery peels back another layer of this enigma. The more we learn, the clearer it becomes. Dark matter isn't just a passive backdrop to our cosmic story. It may very well be the unseen hand that wrote the conditions for life into existence. Whether by accident or design, one thing is certain: our ability to ponder these questions at all might depend on the very mysteries we're trying to solve. Astronomers are locked in a high-stakes debate over one simple number: how fast the universe is expanding. This value, called the Hubble constant, should be the same no matter how we measure it. Yet here we are, with two gold standard methods giving wildly different answers, leaving scientists staring at their equations like detectives at a crime scene where the clues refuse to add up. But hidden in this cosmic discrepancy might be the fingerprint of dark matter's secret behavior. The tension starts with how we measure cosmic expansion. One approach uses the cosmic microwave background, the afterglow of the Big Bang, as a cosmic ruler. By analyzing its subtle fluctuations, scientists can calculate how quickly the early universe grew, arriving at an expansion rate of about 67 kilometers per second per megaparsec. But when we measure nearby stars and supernovas, the rate jumps to 73. That 6-unit gap might sound small, but in cosmology, it's a chasm, one that can't be chalked up to measurement error. It's like checking your speedometer against roadside markers and finding your car is somehow going 2 different speeds at once. This is where dark matter enters the stage. If dark matter particles can interact with themselves or decay over time, it could subtly alter how gravity shapes the cosmos, throwing off our expansion measurements. Imagine inflating a balloon with patches of slightly stretchier rubber. Those regions would expand faster, distorting the overall rate. Self-interacting dark matter could create similar cosmic unevenness, with particle collisions transferring energy that mimics an accelerated expansion in certain regions. Alternatively, if dark matter decays into lighter particles, its gravitational grip would weaken over cosmic time, potentially explaining why local measurements show a faster expansion than those based on the early universe's snapshot. The implications are staggering. If dark matter isn't the stable, inert substance we've assumed, but something dynamic, changing form or interacting invisibly, it would revolutionize our understanding of everything from galaxy formation to the universe's ultimate fate. Some models even suggest dark matter could transition between phases, like steam condensing into water, with these shifts driving variations in cosmic expansion. Others propose dark matter might interact with dark energy, the mysterious force accelerating the universe's growth, creating a feedback loop that skews our measurements. Yet for all its explanatory power, this idea remains controversial. Skeptics argue that tweaking dark matter's properties to fix the Hubble tension might just be swapping one mystery for another. After all, we've never directly detected dark matter particles, let alone confirmed they can decay or collide. It's like diagnosing a car's engine trouble by inventing a new type of fuel, possible but unproven. What makes this mystery so electrifying is that it pits cosmology's most sacred principle, the uniformity of physical laws across space and time, against the enigma of dark matter's true nature. If the Hubble tension disappears with better data, we'll breathe a sigh of relief. But if it persists, we may be staring at the first cracks in our understanding of the invisible universe, forcing us to rewrite the rules of how dark matter shapes the cosmos. The numbers don't lie, but they might be whispering secrets we're only beginning to decode. Hidden in the constellation Coma Berenices lies a cosmic paradox, Dragonfly 44, a galaxy so faint it was overlooked for decades, yet so massive it shouldn't exist. This ghostly smudge of light, discovered in 2016, contains barely a wisp of stars, just 1% the stellar population of the Milky Way, but weighs as much as 1 trillion suns. The difference, 99.99% of its mass, is invisible, making Dragonfly 44 the darkest galaxy ever found. It's like stumbling upon a near-empty warehouse that somehow requires a freight train to budget, a place where the scaffolding outweighs the building by a factor of 10,000. What makes Dragonfly 44 so baffling isn't just its dark matter dominance, but how it defies expectations for galaxy formation. According to standard models, galaxies with such sparse stars should be fragile, their weak gravity unable to hold onto gas or resist tidal forces from neighbors. Yet here's Dragonfly floating serenely in a galaxy cluster, its stars moving so fast they should have escaped long ago, unless an immense halo of dark matter cages them in. Even more perplexing, the stars it does have are ancient, suggesting this galaxy stopped forming new stars nearly 10 billion years ago, freezing in time like a cosmic fossil. Theories about its origins range from the mundane to the extraordinary. One possibility is that Dragonfly 44 was once a normal galaxy, its gas stripped away by violent encounters in the crowded Coma cluster, leaving behind only its dark matter skeleton. Picture a fruit tree ravaged by storms, the fruit stars and leaves, gas blown away, leaving only the gnarled trunk dark matter standing. But simulations struggle to explain how such a process could leave the galaxy's dark halo intact while removing nearly all its visible matter. Another, more radical idea suggests Dragonfly might be a pure dark matter structure that accidentally captured a handful of stars, less a failed galaxy than a dark matter avalanche that swept up stellar stragglers. If true, it would imply the universe contains legions of similar invisible giants, their presence betrayed only by the occasional star or two caught in their gravitational web. Some researchers have even proposed that ultra-diffuse galaxies like Dragonfly could be the missing satellite galaxies predicted by cold dark matter theory, their stars so spread out we've only begun to notice them. The most tantalizing clue lies in Dragonfly's dark matter distribution. Unlike the Milky Way's roughly spherical halo, Dragonfly's invisible mass seems stretched into an elongated shape like a colossal cosmic taffy pull. This could hint at dark matter's ability to clump differently depending on environment, perhaps behaving more like a fluid in low-density regions, allowing it to deform under tidal forces without breaking apart. If confirmed, it would mean dark matter isn't just a passive spectator to cosmic evolution, but an active participant whose behavior changes based on its surroundings. Upcoming telescopes like the Vera Rubin Observatory will scan the skies for more of these shadowy giants, testing whether Dragonfly is a freak outlier or the tip of an invisible iceberg. Either way, its existence forces us to confront a humbling truth. If a galaxy can be 99.99% invisible and still function, how much of the universe's true nature are we still blind to? The Planck satellite, humanity's most precise mapmaker of the cosmic microwave background, revealed the universe's baby picture in exquisite detail, but buried in its data lurked something peculiar. Tiny temperature fluctuations in this primordial light didn't quite match predictions, showing odd asymmetries and unexpected cold spots that refused to fit into our standard models. These anomalies are so subtle they might be statistical noise, or they could be the first whispers of dark matter's true nature, etched into the fabric of space-time itself. One of the most tantalizing discrepancies appears when comparing opposite hemispheres of the sky. The cosmic microwave background should look statistically identical in all directions, a hallmark of the universe's uniformity. Yet Planck's data shows one half of the sky slightly cooler than the other, as if some invisible hand had brushed against the cosmos in its infancy, the odds of this happening by random chance. Less than 1 in 1,000, some theorists suggest this hemispheric asymmetry could stem from dark matter's uneven distribution in the early universe, creating gravitational tugs that subtly warp the cosmic microwave background like fingerprints on a balloon. Then there's the mysterious cold spot, a region spanning hundreds of millions of light years where temperatures dip far lower than models predict. While some dismiss it as a cosmic coincidence, others see it as potential evidence of dark matter's shadowy interactions. If certain dark matter particles can collide and annihilate, releasing energy, they might have left behind localized cooling imprinted on the cosmic microwave background. Picture an ice cube dropped into a warm bath. The surrounding water chills briefly before equalizing. On a cosmic scale, such an event could explain the cold spot's presence, a fossilized relic of dark matter's invisible fireworks. But the plot thickens with Planck's measurements of gravitational lensing, the bending of light by mass. The satellite detected slightly stronger lensing distortions than expected, hinting at extra clumps of mass not accounted for by visible matter alone. Intriguingly, this excess aligns with regions where dark matter simulations predict dense filaments of the cosmic web. It's as if the universe's invisible scaffolding is subtly flexing its gravitational muscles, leaving faint warps in the oldest light we can see. Critics argue these anomalies might vanish with better data, artifacts of measurement errors or incomplete models rather than new physics. After all, the cosmic microwave background is a faint signal buried under interference from galactic dust and other foreground noise. But supporters counter that multiple independent observations, including those from NASA's WMAP satellite, have found similar inconsistencies. If dark matter is indeed responsible, its particles may possess properties far stranger than we've imagined, perhaps interacting through unknown forces or even leaving quantum imprints on spacetime during the universe's first moments. The stakes couldn't be higher. If these anomalies are real, they might point toward a dark sector of physics, a hidden realm where dark matter particles interact with each other via their own invisible forces, like shadows dancing to music we can't hear. Some models propose dark photons or other exotic carriers mediating these interactions, which could subtly alter how dark matter clusters and behaves. Others speculate the anomalies stem from dark matter's quantum entanglement in the early universe, leaving ghostly correlations in the cosmic microwave background that Planck inadvertently captured. Future missions like the Simons Observatory and CMBS-4 will scan the skies with even greater precision, hunting for corroborating patterns. Until then, Planck's anomalies remain cosmic Rorschach tests, glimpses of something lurking just beyond our understanding. Whether they're statistical mirages or the first cracks in our model of the invisible universe, one thing is certain: the answers, when they come, will rewrite the rules of reality itself. According to our best simulations, dark matter should be clumpy like lumpy gravy swirling through the cosmic web. At large scales, it perfectly matches observations, gathering in vast filaments where galaxies cluster. But zoom in closer and things get strange. Instead of dense pockets pockmarking space, smaller regions appear suspiciously smooth, as if some invisible hand has been ironing out the wrinkles. This mismatch between prediction and reality is called the small-scale crisis, and it's forcing scientists to reconsider everything they thought they knew about the universe's hidden skeleton. Take dwarf galaxies, for instance. Cold dark matter models predict these tiny galaxies should be packed with dense dark matter clumps near their cores. Yet observations show their inner regions are far less concentrated than expected, almost as if the dark matter has been gently stirred, smoothing out its distribution. It's like expecting a scoop of Rocky Road ice cream and finding it mysteriously blended into soft serve. One possible explanation: baryonic feedback, a fancy term for how ordinary matter pushes back against dark matter's pull. When stars form and explode as supernova, their fierce winds can blow gas outward, dragging dark matter along like leaves caught in a hurricane. Over time, this process might redistribute dark matter, erasing the smallest clumps. But there's a problem. Some ultra-diffuse galaxies float in near-total isolation, far from the star-forming chaos that triggers baryonic feedback. These cosmic loners should preserve dark matter's primordial clumpiness untouched, yet they, too, appear smoother than predicted. This has led researchers to an even wilder idea. Maybe dark matter isn't cold and sluggish at all, but fuzzy. In this scenario, dark matter particles could behave less like discrete bullets and more like ripples on a pond, their quantum wavelengths smearing out over light years. This fuzziness would prevent dark matter from clumping tightly on small scales, naturally explaining the smoothness we observe. The implications are profound. If dark matter is truly fuzzy, it would mean this invisible substance obeys quantum rules we've never directly observed at such massive scales. Some theories even suggest fuzzy dark matter could consist of ultralight particles, each weighing less than a billionth of an electron. These featherweight particles would zip through space at near light speed, their wave-like nature preventing them from settling into dense knots. Picture trying to build a sandcastle with flour instead of sand. The grains are simply too fine to hold any structure. Yet not all clues point to fuzziness. Certain galaxies show evidence of both smooth and clumpy distributions, as if dark matter's behavior changes depending on its environment. Could there be multiple types of dark matter, some cold and clumpy, others warm or fuzzy? Or are we missing something fundamental about how gravity operates at these scales? Modified gravity theories offer an alternative, arguing that dark matter's apparent smoothness stems from gravity itself weakening slightly in low-density regions. But these models struggle to explain cosmic phenomena like the bullet cluster, where dark matter's gravitational fingerprint is unmistakable. The hunt for answers is pushing telescopes to their limits. Astronomers now scrutinize the faintest dwarf galaxies for traces of microclumps, while particle accelerators hunt for signs of fuzzy dark matter's hypothetical particles. Each observation tightens the noose around potential explanations, but the mystery only deepens. Whether the solution lies in baryonic feedback, quantum fuzziness, or something even stranger, one thing is clear: dark matter's elusive nature continues to defy our cosmic expectations, revealing gaps in our understanding as vast as the voids between galaxies. The Andromeda Galaxy, our Milky Way's closest cosmic neighbor, has always been a benchmark for understanding how spiral galaxies form and evolve. But recent observations have thrown astronomers into a spiral of their own because Andromeda seems to be missing something crucial. Dark matter, the invisible glue thought to hold galaxies together, appears to be in shockingly short supply here. Measurements suggest Andromeda's halo contains only about half the dark matter predicted by simulations, as if someone siphoned off its shadowy foundation without leaving a trace. This cosmic shortfall is especially puzzling because Andromeda isn't some isolated oddball. It's a textbook-perfect spiral galaxy, the kind that should fit neatly into our models. One leading theory points to tidal stripping, a process where gravitational interactions between galaxies slowly steal away their dark matter like thieves in the night. Over billions of years, close encounters with smaller satellite galaxies, or even an ancient brush with the Milky Way, might have tugged Andromeda's dark halo apart, scattering its invisible mass across intergalactic space. Picture two dancers twirling too close, their flowing skirts tangling and tearing. In this case, the skirt is dark matter, and the dance partners are galaxies caught in a gravitational waltz. Yet skeptics argue the anomaly might not lie in Andromeda's structure, but in our measurements. Tracking dark matter's distribution relies on observing the speeds of stars and gas clouds at a galaxy's edges, where visible matter thins and dark matter's pull dominates. But Andromeda's sheer size, nearly twice the Milky Way's diameter, makes these outer regions fiendishly difficult to map. It's like trying to gauge the weight of an iceberg by only studying its tip. Some researchers suggest that overlooked factors, like the galaxy's complex internal dynamics or undetected gas clouds, could be skewing the data, making dark matter seem scarcer than it truly is. The plot thickens when we compare Andromeda to other galaxies. Most spirals its size show dark matter densities that align neatly with predictions, leaving Andromeda as a glaring exception. If tidal stripping is to blame, why don't we see similar deficits in galaxies like the Pinwheel or Triangulum, which have also endured cosmic close calls? This inconsistency has led to a radical alternative. Perhaps Andromeda never had much dark matter to begin with. Some simulations hint that under rare conditions, galaxies could form with naturally sparse halos, flukes of cosmic probability that challenge our assumptions about dark matter's universal role. The stakes are high because Andromeda isn't just another galaxy, it's on a collision course with the Milky Way. If its dark matter content is truly anomalous, the eventual merger billions of years from now might unfold differently than models predict. Future telescopes like the Nancy Grace Roman Space Telescope will scrutinize Andromeda's outskirts with unprecedented precision, hunting for traces of its missing mass. Until then, this cosmic riddle serves as a humbling reminder. Even our nearest galactic neighbor still guards secrets that could reshape our understanding of the invisible universe. Right now, as you sit watching this video, an invisible tsunami of dark matter is crashing through your body at nearly 500 kilometers per second. This isn't science fiction, it's the S1 stream, a vast river of stars and dark matter torn from a dwarf galaxy our Milky Way devoured billions of years ago. Astronomers call it the dark matter hurricane, and its discovery has electrified the search for this elusive substance, offering what might be our best shot at finally detecting the undetectable. What makes this cosmic current so special is its trajectory. Unlike most dark matter, which swirls around us in a roughly spherical halo, the S1 stream barrels through the solar system at a steep 60-degree angle, creating a dense, head-on collision course with Earth. Imagine standing in a quiet forest when suddenly a gale force wind roars through the trees. That's the kind of concentrated dark matter flux we're experiencing right now. For detectors buried deep underground, this hurricane could provide up to a 50% boost in potential interactions, turning what was once a needle in a haystack search into something closer to finding a needle in a smaller haystack. But here's where things get even more intriguing. If dark matter particles have even slight interactions beyond gravity, perhaps bumping into atomic nuclei or releasing faint flashes of light, this stream offers an unprecedented opportunity to spot them. Current experiments like XENO-NNT and LUX-Zeppelin are fine-tuned to catch such rare events, their vats of liquid xenon acting as ultra-sensitive dark matter fishing nets. The hurricane's unique directionality could help distinguish true dark matter signals from background noise, like tracking a specific fish's wake in a crowded pond. Some theorists speculate that if dark matter particles possess unexpected properties, like a tiny electric dipole moment or the ability to exchange dark photons, this concentrated flow might amplify those subtle effects to detectable levels. Yet the S1 stream isn't just a scientific gift, it's also a puzzle. The shredded dwarf galaxy that spawned it contained far fewer stars than expected for its dark matter content, suggesting its original halo was anomalously dense. This raises a tantalizing question. Could certain types of dark matter clump more efficiently in dwarf galaxies, leaving behind these ultra-dense streams when torn apart? If so, studying the hurricane's structure might reveal that dark matter isn't a single, uniform substance, but a family of particles with diverse behaviors. It's like discovering that what you thought was plain water is actually a mix of liquids with different viscosities, each leaving distinct traces as they flow. The most mind-bending possibility, this stream might already have left fingerprints we've missed. In 2015, researchers analyzing gamma-ray data from the Milky Way center found an excess that some attributed to colliding dark matter particles. Though controversial, the signal's energy spectrum curiously aligns with predictions for certain dark matter models, and the S1 stream passes right through that region. Could we have been staring at indirect evidence of the hurricane all along, mistaking its whispers for background noise? Future observations with gamma-ray telescopes like the Cherenkov Telescope Array may settle the debate, scanning the stream's path for telltale flashes of annihilating particles. Whether the dark matter hurricane leads to a historic detection or simply deeper mysteries, its existence reminds us that we're not passive observers of the cosmos, we're immersed in its dynamics, buffeted by invisible currents older than Earth itself. Every second, trillions of these phantom particles from a long-dead galaxy streak through you unnoticed. The only question is whether our experiments will finally catch one, and what that might reveal about the hidden architecture of reality. The James Webb Space Telescope was supposed to bring the universe's earliest galaxies into focus instead. It shattered our understanding of cosmic dawn. Peering back to within a mere 300 million years after the Big Bang, JWST found galaxies not as infantile smudges of light, but as fully fledged cosmic titans, packed with hundreds of billions of stars and weighing more than entire galactic clusters should at that age. It's like archaeologists digging up primordial ruins and finding a gleaming skyscraper where a mud hut should be. These galaxies didn't just break the rules, they threw the rulebook into a black hole. At the heart of this mystery lies dark matter's role as the universe's ultimate timekeeper. According to standard models, these early galaxies simply couldn't have had enough time to accumulate so much mass. Dark matter halos should have needed billions of years to grow massive enough to pull together the gas required for such staggering star formation. Yet these JWST upstarts achieved it in a cosmic blink. One radical explanation: dark matter in the early universe might have been fundamentally different, perhaps denser or more prone to clumping. Picture two types of glue, one that sets slowly over hours and another that bonds instantly. If certain regions of the young universe contained a fast-acting variety of dark matter, it could have jump-started galaxy formation in ways we never anticipated. Another possibility is even more mind-bending. What if dark matter isn't a single substance but has multiple phases or types? Some theories propose a fraction of dark matter might be heavy, with particles 1,000 times more massive than typical predictions. These behemoths would collapse into dense knots almost immediately after the Big Bang, creating gravitational wells deep enough to funnel ordinary matter into premature galaxies. It's the difference between building a city on flat land versus starting with a pre-dug canyon. The foundation's shape changes everything. Yet not all scientists are convinced dark matter needs reinventing. Alternative explanations point to the messy physics of star formation itself. Maybe the first stars burned hotter and died younger than we thought, seeding the cosmos with heavy elements that turbocharged later stellar birth. Or perhaps supermassive black holes formed first, their violent accretion spewing radiation that compressed nearby gas into stars at unprecedented rates. These scenarios still require dark matter's gravitational scaffolding, just not in exotic new flavors. The debate highlights a tantalizing crossroads in cosmology. JWST discoveries could mean dark matter is stranger than we dreamed, interacting with itself or ordinary matter in ways that rewrite galactic evolution. Or they might reveal gaps in our understanding of how visible matter behaves under extreme conditions. Both paths lead to the same unnerving truth. The universe's first chapters contain plot twists we're only beginning to decipher. As JWST peers even deeper into cosmic dawn, each new observation forces us to confront how little we truly understand about the invisible forces that shaped our existence. Could dark matter have killed the dinosaurs? It sounds like science fiction, but a provocative theory suggests our galaxy's invisible scaffolding might be a silent serial killer, triggering mass extinctions by hurling comets toward Earth every 30 million years or so. The idea hinges on a hypothetical structure called the dark disk, a dense plane of dark matter that some models predict should exist alongside the Milky Way's visible spiral arms. As our solar system bobs up and down through this disk during its galactic orbit, the extra gravitational tug could disturb icy bodies in the Oort cloud, sending them raining inward as planet-threatening comets. This controversial hypothesis gained traction when researchers noticed a curious pattern in Earth's geological record. Fossil evidence reveals pulses of increased extinction rates occurring roughly every 26 to 30 million years, a rhythm that eerily matches our solar system's vertical oscillation through the galaxy. It's as if Earth's biosphere keeps time to some cosmic metronome, with catastrophes striking like clockwork. Proponents argue the dark disk provides the missing mechanism, its periodic gravitational nudges acting like a sniper's scope aligning with Earth's position in the galactic cycle. But not everyone's convinced. Critics point out that no direct evidence confirms the dark disk's existence. While certain modified gravity models predict such structures, mainstream cold dark matter simulations show Milky Way-like galaxies forming spherical halos, not dense disks. The difference is like comparing a frisbee to a basketball, both round, but one's thickness changes everything. Even if a disk exists, calculating its precise gravitational influence remains fraught with uncertainty. Some simulations suggest its effect would be too weak to noticeably perturb the Oort cloud, like trying to steer a cruise ship by blowing on its sails. The plot thickens when we examine alternative triggers for periodic extinctions. Earth's journey through the galaxy also takes us through spiral arms, where dense molecular clouds and increased supernova rates could bombard our planet with radiation no dark matter required. Other studies propose volcanic activity or internal climate cycles as potential culprits. The challenge, disentangling these overlapping rhythms, is like trying to identify which instrument in an orchestra played a wrong note 300 million years ago. Yet the theory's most tantalizing aspect isn't just about dinosaurs. It hints at dark matter's potential to shape life's trajectory on galactic timescales. If true, it would mean the universe's invisible majority doesn't just sculpt galaxies, but actively participates in biological evolution. Future telescopes mapping the Milky Way's gravitational microlensing signatures may finally confirm or debunk the dark disk's existence. Until then, this cosmic whodunit remains open, a reminder that even Earth's history might be written in the ink of shadows. Stretching across billions of light years, cosmic voids are the universe's emptiest neighborhoods, gaping regions where galaxies are scarce and darkness reigns. Yet these apparent wastelands may hold the key to one of cosmology's greatest puzzles, the violent cosmic tug of war between dark matter and dark energy. While dark matter's gravitational pull sculpts galaxies into being, dark energy seems hell-bent on tearing them apart, an opposition that reaches its most dramatic climax in these desolate expanses. What makes voids so extraordinary is how they amplify dark energy's influence. In galaxy-rich regions, dark matter's gravity dominates, holding structures together against dark energy's outward push. But inside voids, where matter is thousands of times sparser, dark energy operates unchecked, accelerating the expansion of these emptinesses like cosmic bubble wrap inflating at ever-increasing speeds. The consequences are staggering. Some voids now grow so fast that their edges rush outward at nearly the speed of light, carrying galaxies along like surfers caught on an impossible wave. This runaway expansion presents a glaring contradiction. Standard cosmology assumes dark energy behaves like Einstein's cosmological constant, a steady force permeating space uniformly. Yet the blistering growth of voids suggests something far stranger. That dark energy might grow stronger in low-density environments, its repulsive force dialing up where matter is scarce. It's as if the universe has an unseen dimmer switch, turning dark energy's intensity higher in its emptiest rooms. Some theorists propose this could mean dark energy interacts with dark matter after all, an idea once considered heretical. Picture two invisible dancers. One dark matter tries to cluster everything together, while the other dark energy pushes things apart, but only when they're far enough apart to stop stepping on each other's toes. The implications could rewrite cosmic history. If dark energy's strength varies based on local density, it would mean the universe's expansion isn't just accelerating, it's doing so unevenly, with voids becoming ever more dominant as matter congregates into isolated islands. Extend this process far enough into the future, and the result is chilling. a Big Rip scenario where even atoms get torn apart by runaway expansion. Yet skeptics argue these observations might reflect our limited view. Mapping void dynamics requires painstaking measurements of galaxy motions at unprecedented scales, a task plagued by observational biases. Others suggest alternative explanations, like primordial magnetic fields or quantum fluctuations left over from the Big Bang, could mimic dark energy's apparent strengthening in voids. The truth may lie in upcoming experiments. The Dark Energy Spectroscopic Instrument is creating 3D maps of millions of galaxies, tracing how voids distort spacetime on scales never before measured. Meanwhile, radio telescopes like the Square Kilometre Array will hunt for subtle distortions in the cosmic microwave background caused by void edges moving at relativistic speeds. Whether voids prove to be dark energy's playground or reveal entirely new physics, one thing is certain: in the universe's emptiest places, we're finding clues to its most fundamental forces. The silence of the void may yet speak volumes about the nature of reality itself. At the quantum scale, particles behave in ways that defy common sense, existing in multiple states at once until observed, then choosing a single reality the moment we measure them. This wave function collapse, one of quantum mechanics' deepest mysteries, bears an uncanny resemblance to dark matter's elusiveness. Both phenomena taunt us with their invisibility, revealing just enough to confirm their existence while withholding the crucial details that would explain their true nature. Could the two riddles be connected? Some daring theorists suggest that dark matter might not just be hidden, it could be unseeable by design, veiled by the same quantum weirdness that governs the subatomic world. Imagine dark matter particles don't merely ignore light and matter, but exist in a perpetual state of quantum superposition, their very position and momentum undecided until something interacts with them. In this scenario, our detectors fail not because the particles are too faint, but because they're fundamentally indeterminate, flickering in and out of measurable existence like cosmic ghosts. It's the ultimate shell game. The universe might be teeming with dark matter, but the act of observation could collapse its wave function into states our instruments can't register. This idea finds eerie support in certain modified quantum theories, where consciousness itself plays an active role in shaping reality. If human observation influences quantum outcomes, could the same principle apply to dark matter's invisibility? Might it be hiding in plain sight, not from our technology, but from our awareness? Others take the quantum connection even further, proposing dark matter could be a macroscopic manifestation of quantum entanglement. Just as entangled particles instantly influence each other across vast distances, dark matter might communicate through a hidden network of quantum links, weaving the cosmic web not with gravity alone, but with some undiscovered non-local connection. Picture the universe as a vast quantum computer, with dark matter acting as its entangled qubits operating behind the scenes to maintain cosmic structure in ways that defy classical physics. This could explain why dark matter's distribution appears so eerily uniform across galactic scales, as if guided by a hidden algorithm rather than random chance. Not all physicists embrace such radical ideas. Critics argue that quantum effects typically vanish at larger scales, making it unlikely they'd influence galaxy-sized structures. Yet dark matter's refusal to fit neatly into either the quantum or classical boxes suggests our categories might be too rigid. After all, if quantum mechanics governs the small and relativity, the large dark matter could be the missing link bridging the two, a substance that doesn't play by either set of rules exclusively. The most thrilling possibility, dark matter's quantum nature, might explain why it's proven so hard to detect. If its particles exist in superpositions that collapse only under specific, undiscovered conditions, our current experiments could be like microphones trying to record silence. Future detectors might need to ask the right quantum question, perhaps by exploiting entanglement or quantum coherence, to finally catch dark matter in the act. Until then, this intersection of the universe's biggest and smallest mysteries reminds us that reality's deepest secrets often lurk where we least expect them. One of the most baffling numbers in cosmology isn't some complex equation, it's a simple ratio, 5:1. That's how much dark matter outweighs normal matter in the universe, a proportion so consistent it shows up everywhere we look, from galaxy clusters to the cosmic microwave background. This isn't just statistical noise, it's a cosmic constant screaming for explanation. Why 5 times more dark matter than protons, neutrons, and electrons? And more puzzling, why does this ratio hold so steadfastly across the cosmos, as if some unseen law stamped it into the fabric of reality? Digging into this mystery reveals just how strange the situation is. When we calculate the amount of normal matter from the Big Bang's nuclear reactions and compare it to dark matter's gravitational pull, the 5:1 ratio emerges again and again. It's like checking different rooms in a house and finding every light switch set to the exact same dimmer setting. This consistency spans billions of light years and billions of years, an eerie uniformity that defies random chance. If dark matter were just some accident of particle physics, we'd expect wild variations in its abundance relative to normal matter. Instead, we find a universe that seems to have carefully measured out its ingredients, blending shadow and substance in precise proportions. Theories abound, but none fully satisfy. One compelling idea suggests this ratio is a relic from the universe's earliest moments, when dark and normal matter were forged together in the Big Bang's unimaginable heat. In certain particle physics models, dark matter could have been created alongside baryons through interactions we don't yet understand, processes that naturally produced 5 dark particles for every visible one. It's like a cosmic assembly line set to produce exactly 6 widgets total, 5 black ones and 1 white. But what tuned this hypothetical production line so precisely? Some researchers speculate unknown symmetries or conservation laws might govern the balance, hidden dimensions of physics we've yet to uncover. Another angle points to dark matter's potential influence on normal matter's formation. If dark matter particles interacted with early universe plasma in specific ways, perhaps mediating the formation of protons and neutrons, they might have effectively locked in this ratio during the universe's first seconds. Picture 2 dancers influencing each other's moves until their rhythm synchronizes perfectly. The catch: we've never detected dark matter interacting with normal matter through any force except gravity, making this elegant idea frustratingly difficult to test. Perhaps most mind-bending is the possibility that this ratio isn't fundamental at all, but the result of a selection bias in a multiverse. In countless other universes with different ratios, galaxies might never have formed, meaning we live in one of the rare realities where the numbers allowed life to emerge. It's the ultimate cosmic catch-22. The 5:1 ratio might explain our existence, while our existence prevents us from observing any other ratios. Future particle colliders or quantum gravity experiments could crack this puzzle wide open, or deepen it beyond our current imagination. Either way, this deceptively simple number stands as one of cosmology's most profound clues, hinting that dark matter's story is inextricably woven with our own. Galaxies don't drift through the cosmos in isolation, they collide, merge, and reshape themselves in violent dances choreographed by dark matter's invisible hand. These cosmic crashes should be chaotic, with stars and gas sent careening in all directions. Yet something peculiar happens during these mergers. The galaxy's dark matter halos, like phantom partners in a gravitational tango, glide through the chaos unscathed, holding everything together even as visible matter is ripped apart. The antennae galaxies, one of the most studied merging pairs, reveal this paradox in stunning detail. Their spiral arms stretch into long, luminous streams, a testament to the brutal gravitational forces at play. But the dark matter, it barely flinches, maintaining its distribution as if the collision were nothing more than a gentle bump. Here's where the mystery deepens. If dark matter interacts only through gravity, its halos should pass through each other like ghosts, leaving the visible carnage untouched. Yet observations suggest something subtler is at work. In some mergers, like the Bullet Cluster, dark matter clearly separates from the gas, lagging behind like a shadow. But in others, like the antennae, it clings stubbornly to the galaxy's cores as if tethered by some unseen force. This inconsistency has physicists scrambling for explanations. Could dark matter particles occasionally collide, creating friction where none should exist? Or do magnetic fields in the galaxy's gas influence dark matter's behavior in ways we haven't accounted for? One radical theory proposes that dark matter isn't completely inert. It might possess a tiny electric dipole moment, allowing it to interact weakly with electromagnetic fields. Picture a dancer whose costume billows just slightly in the wind, imperceptible unless you're looking closely, but enough to alter their movement. If true, this would mean dark matter isn't just a passive spectator to galaxy mergers but an active participant, its behavior shifting depending on the environment. The stakes are high because mergers aren't just cosmic spectacles, they're the universe's primary method of building galaxies. If dark matter's role in these events is more complex than we thought, it could rewrite our understanding of how every galaxy, including our own Milky Way, came to be. Upcoming telescopes like the Vera Rubin Observatory will map millions of mergers in unprecedented detail, hunting for patterns that might finally unravel this shadowy puzzle. Until then, each colliding galaxy pair serves as a reminder. The universe's most dramatic transformations often hinge on forces we can't see. What if dark matter doesn't exist at all? That's the radical question behind modified Newtonian dynamics, or a theory that's been quietly challenging cosmology's status quo for decades. Instead of invoking invisible particles, Mann proposes a simpler fix: tweak the laws of gravity themselves. The idea sprang from astronomer Mordechai Milgrom's frustration in the 1980s. He noticed that in the faint outskirts of galaxies, stars move faster than Newton's equations predict, but their speeds followed a peculiar pattern. Rather than requiring dark matter's extra gravity, Milgrom found adjusting gravity's math to weaken slightly at extremely low accelerations could perfectly match the observations. It was as if the universe had a hidden speed bump no one noticed before, subtly altering how gravity works where its pull becomes featherlight. For spiral galaxies, Mann works shockingly well, often better than dark matter models. Take the ultra-diffuse galaxy NGC 1052, where stars orbit so slowly they should fly apart. Dark matter simulations struggle to explain its fragile structure, yet Mann modified gravity predicts its rotation curve with eerie precision. Proponents argue this elegance means we're overcomplicating things. Why invent an invisible substance when a minor gravity adjustment solves the puzzle? But critics pounce on Mann's Achilles heel: galaxy clusters. These massive structures contain so much hot gas that their visible matter alone can't account for their gravitational lensing effects, the way they bend light from background objects. Dark matter neatly fills this gap, while Mann requires additional unseen mass anyway, undermining its no dark matter promise. The debate reached fever pitch when the Hubble Space Telescope mapped the Pandora cluster, a cosmic collision of 4 galaxies. Its gravitational lensing revealed mass distributed exactly where dark matter models predicted, separate from the visible gas, just like the Bullet Cluster. Mann supporters scrambled to explain this without invoking dark matter, suggesting hypothetical hot gas or neutrino-like particles, but Occam's razor started looking dull. If you need exotic matter anyway, why not embrace dark matter's simpler, more comprehensive framework? Recent breakthroughs have only deepened the divide. The European Space Agency's Euclid telescope recently released precision maps of galactic lensing at unprecedented scales. The data reveals a cosmic web of gravity that aligns perfectly with dark matter simulations down to the subtlest filamentary structures. Man struggles to replicate this intricate large-scale architecture without cumbersome additions. Yet it still nails certain small-scale phenomena dark matter can't easily explain, like the tight correlation between a galaxy's visible mass and its rotation speed. The truth might lie somewhere in between. Some theorists now explore hybrid models where gravity behaves unusually and dark matter exists, a compromise that satisfies neither camp but acknowledges both theories' strengths. This tug-of-war isn't just academic, it cuts to the heart of how we do science. Do we preserve gravity's laws by inventing new substances or revise the laws themselves? Both approaches have overturned paradigms before. Neptune was discovered because Uranus' orbit didn't match predictions, validating Newton, but Mercury's wobble required Einstein to rewrite gravity entirely. Today's anomalies, galaxies that spin too fast or too slow, lensing patterns that refuse to fit, might be our generation's Uranus or Mercury. Until one theory explains all the evidence, the phantom of dark matter and the ghostly tweaks of Mund will continue their cosmic dance, each whispering half the truth. Gazing trillions of years into the future, cosmologists face a chilling possibility. Dark matter, the unseen backbone of our cosmos, might be its own executioner. While stars will burn out and galaxies fade, dark matter's ultimate fate could rewrite the universe's final chapter in ways more dramatic than we ever imagined. The conventional view paints a bleak portrait. As dark energy accelerates cosmic expansion, galaxy clusters will grow isolated, their dark matter halos stretched thin across ever vaster voids until gravity's grip becomes too weak to hold anything together. But recent simulations reveal darker, more violent possibilities lurking in the shadows. One nightmare scenario involves dark matter's potential self-destruction. Certain theoretical models suggest that if dark matter particles can decay, transforming into lighter particles or even pure energy, the universe's invisible scaffolding could gradually dissolve over eons. Imagine a bridge where the steel beams slowly rust to dust. First the smaller structures collapse, then the largest. Galaxies would disintegrate from the outside in, their outer stars flung into the abyss as the halo's gravitational glue vanishes. The timeline for this decay remains hotly debated. Some theories place it 100 billion years in the future, others so far ahead that the number of zeros outpaces all the atoms in our galaxy, but the implication is the same. The very substance that birthed galaxies might one day erase them. Yet another apocalyptic vision emerges from the interplay between dark matter and black holes. As stars die and galaxies merge, supermassive black holes will feast relentlessly, growing to unimaginable sizes. These gravitational monsters could gravitationally focus streams of dark matter, creating ultra-dense cusps where dark matter particles collide and annihilate at catastrophic rates. The resulting energy might briefly illuminate the dying cosmos, a final fireworks display in an otherwise lightless era. Or, in a crueler twist, concentrated dark matter could feed the black holes further, accelerating their growth until they dominate entire galactic graveyards. The wild card in all this is dark energy's exponential push. If dark energy strengthens over time, a scenario called phantom energy, it wouldn't just isolate galaxies, it could tear apart dark matter's structure itself. This big rip would see clusters, then galaxies, then stars, and finally atoms torn asunder as expansion outmuscles every fundamental force. Dark matter, though immune to electromagnetism and the strong nuclear force, would still succumb to spacetime's violent stretching. The cosmic web, the grand tapestry dark matter spent billions of years weaving, would unravel thread by thread until nothing remains but solitary particles drifting in an infinite void. Amid these grim forecasts, one radical theory offers a strange consolation. dark matter might orchestrate a cosmic rebirth. If certain extra-dimensional models are correct, decaying dark matter could seed new universes, its particles tunneling through hidden dimensions to spark new Big Bangs. Our universe's death would give rise to countless others, each with its own laws, its own dark matter, its own cycle of creation and destruction. It's a poetic twist for the substance that shaped our existence. In the end, dark matter wouldn't just be part of the universe's story, it might become the author of infinite new ones. For now, these scenarios remain speculative chess games played with mathematical models and incomplete data. But as telescopes probe deeper into dark matter's secrets, each discovery brings us closer to answering humanity's most profound question, not just where we came from, but how the cosmos itself will choose to die. What if dark matter isn't just an inert cosmic ingredient, but a hidden frontier for life itself? This isn't science fiction. Theoretical physicists have begun seriously exploring the idea that dark matter could form complex structures, even self-replicating patterns eerily reminiscent of biological life. The foundation of this radical hypothesis lies in dark matter's potential for variety. Just as ordinary matter comes in protons, electrons, and neutrons that combine into atoms, molecules, and eventually life, dark matter might consist of multiple particle types capable of intricate interactions we can't yet fathom. Picture a shadow biosphere, an entire ecosystem of dark matter organisms drifting unseen through your body right now. These hypothetical entities wouldn't rely on chemistry as we know it. Instead, they might exploit dark forces unknown to standard physics to store information, replicate, and evolve. Some models propose dark photons, hypothetical particles mediating interactions exclusively between dark matter particles, creating a parallel version of electromagnetism. In such a framework, dark matter could theoretically assemble into structures as complex as DNA, powered by flows of dark energy instead of ATP. The most compelling argument for this wild idea comes from nature's tendency toward complexity. Wherever energy gradients exist, from hydrothermal vents to thunderstorms, self-organizing systems emerge. Dark matter's gravitational dance creates its own dynamic landscapes, filaments spinning in vortices, halos with density gradients, even shockwaves from cosmic collisions. These environments could, in theory, harbor the necessary conditions for dark life to arise. Researchers have simulated scenarios where certain types of interacting dark matter form stable, self-replicating patterns, cosmic-scale analogues to crystal growth or cellular automata, but operating on gravitational timescales spanning millions of years. Critics counter that life requires more than just complexity. It needs metabolism, adaptation, and information storage. Yet even here, dark matter surprises us. Certain theoretical constructs called topological defects, knots in spacetime's fabric left over from the Big Bang, could store information in their shapes, evolving as they interact with passing dark matter streams. Others propose that dark matter particles with slight electric dipole moments might form extended structures sensitive to electromagnetic fluctuations, creating a crude form of perception. The implications are staggering. If dark life exists, it would operate on timescales and scales beyond human comprehension, organisms as large as galaxies, metabolizing the slow decay of dark energy over eons. Some might even view the cosmic web itself as a neural network of sorts, with dark matter filaments acting like axons transmitting gravitational signals across the universe. Far-fetched, absolutely, but so was the concept of bacteria before microscopes revealed their world. Our inability to detect dark matter's nuances doesn't negate their potential richness, it merely highlights the limits of our current tools. Whether this hypothesis holds water or evaporates under scrutiny, it serves a vital purpose, stretching our imagination about what life could mean in a universe where 95% of reality remains hidden. After all, if dark matter truly dominates the cosmos, wouldn't it be arrogant to assume nature's creativity stops at the boundary of the visible? What if dark matter isn't just a cosmic mystery, but the hidden code of reality itself? A radical twist on the simulation hypothesis suggests that dark matter's bizarre properties might be the telltale glitches of a programmed universe. Think of it like this. When game developers create virtual worlds, they often add invisible collision boxes to prevent characters from clipping through walls. Dark matter could serve a similar purpose, an unseen framework stabilizing galactic structures in a universe running on some unimaginable quantum processor. This idea isn't as far-fetched as it sounds. The simulation argument, popularized by philosopher Nick Bostrom, posits that advanced civilizations could create ancestor simulations so detailed their inhabitants wouldn't know they're digital. But simulations have limits. Every virtual world requires optimization tricks to handle vast scales like level of detail algorithms that reduce rendering load for distant objects. Dark matter's behavior fits uncannily. Its gravitational effects are flawless at galactic scales, yet up close, it refuses to interact like normal matter. Almost as if it's not a substance at all, but a placeholder to maintain gravity's consistency where computational resources are thin. Critics dismiss this as metaphysics masquerading as physics, and they have a point. Science demands testable predictions, and labeling dark matter as computational padding explains everything and nothing, yet intriguing parallels emerge. In computer science, whenever a simulation needs to conserve processing power, it often approximates physics with statistical shortcuts. Sound familiar? Dark matter's apparent uniformity across the cosmos mirrors how a lazy programmer might reuse the same algorithm everywhere. Even the dark matter to normal matter ratio, that eerily consistent 5-to-1 split, could reflect an optimization choice like default settings in a physics engine. But here's where the theory frays. If our universe was simulated, why would its code leave such obvious artifacts? Wouldn't hyper-advanced simulators hide their tracks better? Proponents counter that dark matter might not be a mistake, but a feature, a deliberate signature. Just as programmers leave Easter eggs in software, our creators might have embedded clues to spark civilizations like ours toward discovery. The cosmic microwave background's anomalies, dark matter's ghostly fingerprints, even the universe's suspiciously perfect fine-tuning for life, all could be breadcrumbs leading to the truth. The debate forces us to confront science's boundaries. While the simulation hypothesis might never meet falsifiability standards, its value lies in questioning assumptions. If dark matter defies every conventional explanation, shouldn't we at least consider unconventional ones? After all, every major scientific revolution began with heresy, from Earth orbiting the Sun to quantum particles existing in multiple states at once. Whether dark matter proves to be particles, gravity's miscalibration, or something far stranger, one thing's certain. Its mysteries continue to expose how little we understand about the fabric of reality, simulated or otherwise. Somewhere beyond the edges of our observable universe, maybe even beyond the boundaries of reality as we know it, other universes might exist with entirely different rules. Dark matter could be the key to understanding why ours seems so perfectly tuned for life. Imagine a cosmic landscape where every possible variation of physical laws plays out, with dark matter's strength flickering like a dial between extremes. In some, it clumps too densely, strangling star formation before life gets a chance. In others, it's too sparse, leaving galaxies to spin apart into cosmic mist. Ours, just right like the universe, hit a bullseye we can't yet explain. This Goldilocks balance isn't just luck, it might be the signature of a deeper multiversal structure. String theory and inflationary cosmology suggest that countless bubble universes could have formed during the Big Bang, each with random variations in fundamental constants. Dark matter's density in our universe, neither so weak that galaxies fly apart nor so strong that they collapse into black holes, could be one such roll of the dice. The eerie precision of this balance has led some physicists to wonder, is our dark matter ratio inevitable, or did we win a cosmic lottery? Take the dark matter to normal matter ratio, that consistent 5-to-1 split that shows up everywhere from galaxy clusters to the cosmic microwave background. In a multiverse, this number wouldn't be fixed. Some universes might have 100 times more dark matter, others almost none. The ones where the ratio falls outside a narrow window would likely be sterile, incapable of forging the stable galactic neighborhoods needed for life. Our universe's just right calibration might simply be survivorship bias. We're here to ponder it because we're in one of the rare bubbles where the numbers lined up. The most compelling clues come from computer simulations. When researchers tweak dark matter's properties, making its particles heavier, lighter, or more interactive, the results are catastrophic. Too much and galaxies drown in dense, starless halos. Too little, and they never form coherent structures at all. Only within a razor-thin range do spiral galaxies like the Milky Way emerge with their orderly arms and stable orbits. It's as if the universe had a checklist for habitability, and dark matter's behavior ticks every box, but the multiverse explanation isn't the only game in town. Skeptics argue that dark matter's fine-tuning might be an illusion, a temporary convergence in a dynamic system. Just as Earth's climate has swung between ice ages and tropical eras over geological time, dark matter's influence could vary across cosmic epochs. What seems perfectly balanced now might have been a chaotic mess billions of years ago, or could become one in the distant future. Others suggest undiscovered laws could lock dark matter's properties into necessity rather than chance, like pieces slotting into a predetermined puzzle. The search for answers is pushing astrophysics into uncharted territory. Future gravitational wave detectors might catch echoes of collisions between our universe and others, while quantum experiments could reveal hidden dimensions where dark matter's secrets are encoded. Until then, the multiverse remains a tantalizing what-if, a lens that transforms dark matter from a cosmic mystery into something even more profound, a fingerprint of realities beyond our own. Whether it's proof of a vast multiverse or just another piece of our universe's unique puzzle, one thing is clear: dark matter's story is far stranger than we ever imagined. From the eerie emptiness of cosmic voids to the violent ballet of colliding galaxies, each of these 25 mysteries peels back another layer of dark matter's profound enigma. We've seen how it warps the Milky Way's halo into a lopsided shadow, how it propels galaxy clusters toward unseen horizons in the dark flow, and how its ghostly presence might have even steered the comet that doomed the dinosaurs. We've puzzled over Planck's anomalies in the cosmic microwave background, those cryptic fingerprints that could rewrite the rules of quantum physics, and grappled with galaxies like Dragonfly 44, where dark matter outweighs stars by a factor of 10,000. And let's not forget the cosmic hurricane of the S1 stream, raining invisible particles through your body at this very moment, or the radical possibility that dark matter itself could be a form of shadow life, thriving unseen in the cracks of reality. Yet for every clue we uncover, the mystery only grows richer. The bullet cluster proved dark matter exists, then showed us how little we understand its behavior. The missing satellite problem revealed gaps in our simulations, while JWST discovery of impossibly ancient galaxies forced us to question dark matter's role in cosmic dawn. Even the precise 5-to-1 ratio of dark to normal matter taunts us with its unnatural perfection, as if the universe encoded a message we're just beginning to decipher. And lurking beneath it all, the haunting question: is dark matter a particle, a flaw in gravity, or something far stranger, a glitch in the cosmic code, a multiversal echo, or even the scaffolding of a simulated reality? What binds these puzzles together isn't just their complexity, it's their defiance of easy answers. Dark matter doesn't merely hide in the shadows, it dances at the edges of our understanding, reshaping its secrets with every discovery. The Vera Rubin Observatory will soon scan the skies for faint dwarf galaxies that could solve the missing satellite crisis. LISA, the space-based gravitational wave detector, might catch whispers of primordial dark matter from the Big Bang. And deep underground, experiments like LUX Zeppelin and Darwin grow ever more sensitive, poised to snag a fleeting collision with this elusive substance. But here's the delicious irony: even if we detect dark matter tomorrow, its deepest truths may still elude us. Does it interact with hidden forces? Could it decay or transform or harbor complexity beyond our imagination? The greatest lesson these 25 mysteries teach us is that the universe loves a good plot twist, and dark matter is its masterpiece, so stay curious. The next chapter of this cosmic detective story might not bring answers, but it's guaranteed to take us deeper into